discussion perhaps during the lunch period. Dr. Marzari? Our next talk. Next talk will be presented by Dr. Marzari, who has just completed his PhD requirements at the University of Louisville. He previously has a petroleum engineering degree from the University of Cuyo in Argentina, and his work experience with Seoul Petroleum Company for a couple of years. His talk today will be on bifunctional mechanism of pyridine hydrogenation. Dr. Marzari.
Thank you. My presentation is, as he said, the bifunctional mechanism of pyridine hydrogenation. So, as an introduction, the availability of clean fuel resources is drastically declining. Nickel and vanadium porphyrins, as well as nitrogen and superorganic compounds, are responsible for environmental pollution, oil hazard, catalytic activation, corrosion, etc. Therefore, the elimination of this impurity is of vital importance in the petroleum and petrochemical industry. Hydrotreatment is a catalytic process in which sulfur, nitrogen, oxygen, and metals are removed in the form of ammonia, hydrogen sulfide, water, from metal-organic compounds present in fuels and synthetic crude. The removal of sulfur is achieved at a large extent, and the catalysis involved is fairly well understood. However, for the elimination of nitrogen compounds, hydrodenitrogenation needs tougher operational conditions to proceed than hydrodesulfurization, and the elimination is not achieved at a large extent. It is known that 6-member nitrogen heterocycles are the most refractory compounds to this type of reactions, and since heteroring hydrogenation is the first reaction step in the elimination of nitrogen, HDN consumes large quantities of hydrogen. In order to remove nitrogen as ammonia, it is necessary to cleave the carbon-nitrogen bond, and there is no agreement in the mechanism of reaction. The rate limiting step of hydrodenitrogenation, either the hydrogenation of the ring or the carbon-nitrogen bond cleavage, depends on the catalytic system and on the operational conditions. So, in the present work, we use pyridine as the probe molecule because it's the simplest 6-member nitrogen heterocycle. Pyridine is hydrogenated partially or totally to piperidine. This is a reversible reaction, and then the first carbon-nitrogen bond cleavage proceeds either by hydrogenolysis or Hoffman elimination, and then the second one that is faster to give pentane plus ammonia. As a review of pyridine hydrodenitrogenation, Cox and Berg were the first ones to study this reaction. McKilber proposed the reaction network that I showed before: pyridine that is transformed into piperidine, into pentylamine, and then into pentane plus ammonia. Sonnemans and Mars studied pyridine, piperidine, and pentylamine hydrodenitrogenation at 60 atmospheric hydrogen. They found a more complex reaction network because of the appearance of disproportionation products. This product did not occur when they were working at atmospheric pressure in hydrogen, and this condition would be later used by Ledoux. Pyridine, piperidine is found at a thermodynamic equilibrium, and this would be later studied in more detail by Coqueto and Satterfield. Line proposed, years later, Line proposed a mechanism for the carbon-nitrogen cleavage following hydrogenolysis on molybdenum-coordinatedly unsaturated sites, while Nelson and Levy, they proposed carbon-nitrogen cleavage following Hoffman elimination, catalyzed on Bronsted acid-Lewis base sites. So then finally Ledoux, he carried out the study of pyridine hydrodenitrogenation, different catalysts, but this wasn't a systematic work. He proposed the mechanism for Hoffman elimination. He tried to verify Hoffman elimination in HDN, So he was able to carry out pyridine denitrogenation and bare alumina. However, there is no convincing evidence that Hoffman elimination really occurs in HDN. There hasn't been any intent to correlate Bronsted acidity and Hoffman elimination. And there hasn't been any systematic work correlated catalyst composition and molybdenum oxide loading in hydrodenitrogenation. So the objectives of the present work are first to prove the feasibility of Hoffman elimination type mechanisms catalyzed of Bronsted acid Lewis base sites. Then to examine the effect of molybdenum oxide loading and support composition on pyridine hydrodenitrogenation activity and selectivity. Then try to correlate the functionalities of the catalyst and the reaction rates. Then to answer the question is to analyze the effect of molybdenum oxide phases previous to the catalyst reduction in the generation of active sites for hydrogenation and hydrogenolysis. And finally, to propose a bifunctional mechanism for pyridine hydrodenitrogenation. The proposed mechanisms for carbon-nitrogen bond cleavage basically are hydrogenolysis, that is suggested to proceed on molybdenum coordinatedly unsaturated sites. Then Hoffman elimination, that is a bimolecular beta elimination that occurs on Bronsted acid Lewis base sites. And then a third mechanism that is nucleophilic attack at the carbon alpha followed by the carbon-nitrogen bond cleavage that occurs in the presence of other nucleophiles such as hydrogen sulfide. Since the present work was carried out in a hydrogen sulfide-free environment, this later mechanism is not going to be considered. Here are the mechanisms. The first one is hydrogenolysis, proposed by Laine, as I referred before, and we can see that it follows a mechanism, a pathway similar to homogeneous catalysis. But I would like to put the attention on the beta of Hoffman elimination. It can be seen that the nitrogen and the beta carbon has an hybridization of sp3. So the proton coming in from the surface quaternizes the nitrogen, and simultaneously a beta proton from the pyridine is attracted by the Lewis base on the surface of the catalyst, and the cleavage proceeds. So in order to study if this mechanism is feasible, we carry out the following experiment. We took silica alumina 75%, 75% silica, 25% alumina, that is known to have large concentration of Bronsted acid sites. For that, we use a diffuse reflectance IR spectrometer equipped with an environmental chamber in which we were able to use different temperatures and different pressures. And this was connected in series with a mass spectrometer. The sample, silica alumina sample, was introduced inside the environmental chamber. The temperature and the vacuum were allowed in order to remove the physics of gases. Then at high temperature, E2 was introduced. So now we changed the OH groups on the surface to OD groups. Then a high vacuum was allowed again, the temperature was lowered. At that point, piperidine was injected under vacuum. It could be seen the interaction of piperidine with those OD groups on the surface by the infrared spectra, and the boiling gases were analyzed by the mass spectrometer. Then the temperature was raised, and again the same analysis was followed. So the goal of this experiment is to see if, because of this interaction of OD groups with piperidine, first of all, is there any exchange? How many exchanges? And in which positions? This is a fragmentation pattern of in a mass spectrometer of piperidine. We can see that the molecular weight of piperidine is 85, and the current peak is 84. What it was observed from the evolving exchange piperidine were the same smaller peaks, but we observe now 3 peaks, 84, 85, and 86. And so answering the question, yes, there is an exchange. How many? 1. Now the problem is in which position. So here is the mechanism of fragmentation of piperidine given by Foster and Baldas. The position could be in the nitrogen, in the alpha carbon, in the beta carbon, or in the gamma carbon. So analyzing all these different mechanisms and their masses, we arrive to the following conclusion. Gas phase represents the regular piperidine. The sword represents the exchange piperidine. We observe 86, delta mass 86. And analyzing those mechanisms of reaction, we arrive to the conclusion that the only position that this exchange could have taken place is on the beta position. And that is in agreement with beta elimination. So what this is saying, that beta elimination or Hoffman elimination is a feasible mechanism. When piperidine is interacting with OH groups on the surface, the beta proton becomes labile. So now the following step is to study how does the acidity, Bronsted acidity, correlates with denitrogenation. So the total acidity was measured by ammoniac chemisorption. Total acidity measures Bronsted acidity and Lewis acidity. So for that, alumina, silica, 5 different silicas aluminas were used, and they were supported with 4, 8, and 12% molybdenum oxide. It was observed that the largest acidity, total acidity, was verified when the silica support composition was 25%. Now, in the study of Bronsted acidity, the chemisorption, the infrared spectroscopy of chemisor pyridine was used, and the Bronsted-Lewis acidity ratio was measured. It was observed that the largest Bronsted-Lewis ratio is achieved when the silica support composition is 75%. This is in agreement with NMR experiments and model reactions. So the piperidine denitrogenation on different silica aluminas, no molybdenum oxide in both, was carried out at 340 degrees in 1 atmosphere of helium. What it can be observed is that the Bronsted-Lewis ratio, and I would say the Bronsted acidity, directly correlates with denitrogenation activity. Summarizing, the denitrogenation activity directly correlates with Bronsted-Lewis ratio and not with total acidity. And what this is saying is that in denitrogenation, the carbon-nitrogen bond cleavage can proceed following a Hoffman elimination mechanism that is catalyzed on Bronsted acid, Lewis phase side, and occurs in parallel to hydrogenolysis of the carbon-nitrogen bond. So, the study of pyridine hydrodenitrogenation, now for catalysts with molybdenum oxide, were the same catalyst for 8% molybdenum oxide loading, the same alumina silicas, 5 different silicas alumina. The reaction was carried out at 1 atmosphere in hydrogen and at 4 different temperatures, 360, 380, 400, and 420 degrees centigrade. It is observed that the largest activity, the largest reaction rates are achieved for silica-supported catalysts, and this was our first surprise because most of the literature refers that the alumina catalysts are more active. But once one checks that literature, all the catalysts are sulfided ones. There is even a case reported by Jermakov who refers that for sulfided nickel molybdenum on silica are more active than those same catalysts on alumina. Neither case applies to the present work. So a hint to understand this behavior is given by Leduc in his review of hydrodenitrogenation, and he suggests that for molybdenum oxide catalysts, no additives, the hydrogenation of the ring is the rate limiting step. So for that, we try to correlate with sites that originate in the reduction of molybdenum oxide. So we try to correlate with extent of reduction of those catalysts. 0 in this case represents the cation, molybdenum cation of class 6. 2 represents the molybdenum cation of class 4. It is observed no correlation. Also, the extent of the reduction for the silica-supported catalyst is much larger than for the alumina-supported ones. And this is logic because alumina interacts more strongly with molybdenum oxide than silica. I'm going to come later to these results. So we tried to, another way to correlate or to analyze the species generated upon reduction is by the technique low temperature oxygen chemisorption developed by Pareto and Weller. This technique is an approaching technique to measure or to assess the amount of molybdenum-coordinated unsaturated sites that are generated upon the reduction of molybdenum oxide. It is observed there is a very nice correlation with the reaction rates. 4% molybdenum oxide, 8 and 12%, and in this case, similar behavior for 8 and 12%. The simplest theory for low temperature oxygen chemisorption refers that one oxygen atom chemisorps or titrates one molybdenum COS. So this following graph is the correlation between that reaction rate and the MOS COS, and it can be observed the reliability of this regression line is around 80%. Though all these points are regardless of port composition and molybdenum oxide loading. The second point, important point, is that the line cuts the y-axis at 0, and what it's saying or representing is that when there is no molybdenum COS on the surface, there is no pyridine HDN, and that is logic because the first step in pyridine HDN is the hydrogenation, and this experiment was carried out and verified. Continuing the analysis of the products of reaction and trying to study the hydrogenation activity, we measured the ratio between the paraffinic and olefinic products. It was observed at 4% molybdenum oxide loading and at 4 different temperatures that the activity for hydrogenation sharply increases for silica support composition above 50%. What else, there is an increase with temperature on the activity towards hydrogenation, and this was our second surprise because if hydrogenation is an ectothermic reaction, we should have expected that the opposite trend. As the temperature increases, the activity decreases. So what this is saying is or implying that that the reaction hydrogenation reaction is not controlled but by thermodynamics, but by kinetics. This is the same result or similar results, but now at 420 degrees for 4, 8, and 12% molybdenum oxide. We also see a sharp increase in the case of for cyclopentene and cyclopentane, and the only non-denitrogenation products were 4 and 2 methylpyridines. It can be observed that below 75% silica, the selectivity doesn't vary, while after above 75% there is a sharp increase, and that the selectivity decreases as the molybdenum oxide loading increases. So in order to explain all these results, we need to analyze the reaction kinetics. Pyridine is hydrogenated to piperidine. This is a reversible reaction, and then piperidine goes into products, and that is an irreversible reaction. So if the carbon-nitrogen bond cleavage is the rate-limiting step, that means that as pyridine-piperidine is found at a thermodynamic equilibrium, and the position of this equilibrium wouldn't affect in large extent the reaction rate toward hydrodenitrogenation. Unfortunately, we were not able to observe piperidine in our products because of the temperature and pressure of the work. Now, if the case is the hydrogenation of the ring is the rate-limiting step, as pyridine-piperidine is not found at a thermodynamic equilibrium, as soon as pyridine is hydrogenated to piperidine, piperidine reacts to give products, and this is what we observed. As the temperature increased, as the activity towards hydrogenation was increasing, also we observed an increase in the reaction, in the overall reaction rate. So these results are suggesting that under the present condition and with the present catalytic system, the rate-limiting step is the hydrogenation of the pyridine. The hydrocracking activity was measured by grouping the different products of reaction by the number of carbon in their molecule. So we have carbon 1, 2, 3, 4, and 5 and methyl pyridines. It is observed once again that above 50% silica, there is a sharp decrease in the formation of carbon 5 and methyl pyridines, while methane increases. I would say that this is mainly attributed to hydrogenolysis. The analysis of isomers of carbon 5, it is observed the main peak attributed to trans-2-pentene, and which sharply decreases at the silica above silica 50%. If we consider that this was the only carbon 5 product observed at low retention times, it can be suggested that it's an important intermediate in the reaction in the hydrodenitrogenation of pyridine. Once again, the correlation between molybdenum COS and the ratio of carbon 5 compounds cracked shows that a regression line with a reliability of 80%, regardless of pore composition and molybdenum oxide loading. And what is also suggesting is that when the amount of molybdenum COS is 0, there is still cracking. So that cracking is acidic. Another way to study the acidic cracking is by comparing the ratio of carbon 4 to carbon 3 compounds. Acidic cracking occurs in the middle of the molecule, while hydrocracking occurs at the end of the molecule. So carbon 4 is mainly formed by hydrocracking, while carbon 3 is formed by hydrocracking of carbon 4 and acidic cracking of carbon 5. So for large molybdenum oxide composition and loadings, the ratio is large, what is saying that the acidic cracking activity is low. For low molybdenum oxide loadings, the ratio is lower, so it's showing that the acidic cracking is high. If we assume that molybdenum oxide at low loading doesn't cover the whole support and the main acidity in the catalyst coming from the support, we can verify that, and also we can verify that the minimum is observed for silica concentration of 50 to 75%. That is the area where the largest Bronsted amount of Bronsted acid sites and concentration is found. So in order to answer on the other objective, how the reduction of molybdenum oxide species generate the different sites for hydrogenolysis and hydrogenation, we have to, this is giving you a summary of TPR annexed at the experiment. I'm not showing them because there is no time, but this is in agreement with literature. There are 4 main species on the surface of silica alumina catalyst: tetrahedral molybdenum oxide, octahedral molybdenum oxide layers, orthorhombic molybdenum oxide crystals, and aluminum molybdate. Tetrahedral molybdenum oxide is mainly formed below 4% molybdenum oxide on alumina because this species is difficult to reduce and is strongly interacting with alumina. This formation gradually decreases as silica concentration in the support increases. For the case of octahedral molybdenum oxide layers, it is formed a larger molybdenum oxide loadings on alumina. It gradually increases as silica concentration increases, and it is formed on silica a low molybdenum oxide concentration, low molybdenum oxide loadings. Orthorhombic molybdenum oxide crystals are found at about 75% silica concentration and above 8% molybdenum oxide loadings. This is questionable, but this is more or less the values. And it's found about 4% molybdenum oxide loading on silica. Finally, we were able to observe aluminum molybdate species generated for silica alumina when the silica composition was 50 to 90%, and for loading above 8% molybdenum oxide. So, summarizing this in the following graph, and these values, they don't have any scientific meaning, just to give an idea. We observed that at low molybdenum oxide loadings, 4%, tetrahedral molybdenum oxide species decreases as the silica support composition increases. The octahedral molybdenum oxide layer increase with the silica and then decrease for pure silica, and we observe the formation of octahedral molybdenum oxide, orthorhombic molybdenum oxide crystals on silica for large molybdenum oxide loadings. We observe lower quantities of concentration of tetrahedral. We observe larger of octahedral. Now we observe the presence of aluminum molybdate species that are occur between 50 to 90% silicate alumina. And then on pure silica we observe mainly orthorhombic molybdenum oxide. So if we consider these ideas, here is again the average oxidation state. On alumina, we observe that as the molybdenum oxide increases, the average oxidation state decreases. It decreases at a lower extent on alumina because of the reduction of tetrahedral molybdenum oxide that is strongly interactive with alumina. In the case of silica-supported catalyst, the reduction is done at a large extent, mainly because of the reduction of orthorhombic molybdenum oxide crystals and some octahedral. Now for silica alumina, we have a combination of, in this area, of orthorhombic molybdenum oxide, mainly octahedral molybdenum oxide, and aluminum molybdate. So if we consider this concept and we try to correlate with the molybdenum COS assessment and the overall reaction rate for between 50 and 90% silica alumina, we don't see a large incidence of the reduction of aluminum molybdate in the generation of oxygen chemisorption species sites. For 4% molybdenum oxide on alumina, that is the main catalyst. For tetrahedral molybdenum oxide. The reduction of that species doesn't generate large quantities of sites for oxygen chemisorption. So what we are concluding of these results are suggesting is that the reduction of octahedral molybdenum oxide layers and the reduction of orthorhombic molybdenum oxide crystals are the main species to generate active sites for hydrogenation and hydrogenolysis, and these sites correlate with the overall reaction rate. So, summarizing, the reduction of aluminum molybdate species that not lead to the formation of oxygen chemisorption sites, nor correlate with HDN activity. The creation of suitable sites for low temperature oxygen uptake that result from the reduction of molybdenum tetrahedral species is substantially poor. And XRD, TPR, and low temperature oxygen chemisorption result suggests that the reduction of both orthorhombic octahedral molybdenum oxide species and orthorhombic molybdenum oxide crystals convey to the generation of oxygen chemisorption sites which correlate with the overall reaction rate. Finally, this is the proposed mechanism for carbon-nitrogen bond cleavage. It's similar to the one that Leduc proposed. Pyridine interacts with the OH groups or the molybdenum COS, then becomes parallel to the surface. The first hydrogenation occurs, the second hydrogenation occurs, and at this stage, the carbon-nitrogen bond cleavage can take place by hydrogenolysis or by Hoffman elimination. This is a mechanism proposed for hydrogenolysis. I'm not going to go in detail. This is the 1,4-beta elimination, which accounts for the generation of trans-2-pentene and the cyclopentene and cyclopentane. Finally, the conclusions. Hofmann elimination is a feasible mechanism in hydrodenitrogenation of pyridine. Under the present conditions, pyridine HDN carried out on supporting molybdenum oxide catalyst show that the heteroring hydrogenation is the rate limiting step of the reaction, and that trans-2-pentene is an important reaction intermediate. Also, molybdenum COS concentration correlates with both the overall reaction rate and the fraction of carbon-5 compounds scrapped, regardless molybdenum oxide loading or support composition. XRD, EPR, and low-temperature oxygen absorption results suggest that oxygen absorption sites are primarily generated upon the reduction of molybdenum octahedral molybdenum oxide layers and orthorhombic molybdenum oxide microcrystals. Finally, a bifunctional mechanism was proposed for pyridine HDN, and I would like to thank the people that have funded the present work, the Department of Energy, the National Science Foundation, and the Commonwealth of Kentucky. Thank you very much.
We do have time for questions.
Some of your mechanisms that needed a pair, a Bronsted site, and a Lewis base.
Yes.
Is that correct?
Yes.
Did you look at your catalyst as far as quantifying the number of basic sites for?
We didn't characterize those basic sites. We didn't.
You said you had proton hydrogen exchange with three positions. Yet the Hoffman elimination is not involved in that first step. Pyridine hydrogenation. Why do you think that happens? You injected the Hoffman elimination as a reason for that exchange.
Okay. What I would like to understand is if Hoffman elimination occurs. So, what is once the Bronsted acid proton from the surface quaternizes the nitrogen, there is an attraction by the Lewis base on the surface from the beta position. So what I wanted to do, or we wanted to do in the experiment, was to observe that because of that interaction, there was a lability of a beta proton in piperidine.
In the experiment, weren't you injecting pyridine into the reactor?
In which one of the experiments? First, when we
were injecting piperidine into
in the first one, when we check only acidity, we were injecting piperidine. Here. In this one is denitrogenation of piperidine. So since we need the hydrogenation of the ring, if we don't have molybdenum COS, we are not going to get any hydrodenitrogenation if we check pyridine. And we verified that because under these same conditions, using, for example, silica alumina 75%, we carry out the denitrogenation of pyridine, and there was none because we don't have molybdenum COS. But for piperidine, yes, there was a correlation between the Bronsted acidity and the denitrogenation activity.
Just for reference, the nickel moly and cobalt moly are the catalysts for industrial use. How do they compare in rates compared to just moly or circle?
It is difficult to say because the conditions of the present work is really different. We work at pressure, hydrogen pressure of 1 atmosphere, while in industry you work at 50 atmospheres. So in order to compare those reaction rates,
Well, I mean, if you put nickel on with your moly, the same conditions, the same everything.
we didn't carry out those experiments.
Is there any reason why you didn't?
We need to keep on working in this area.
Well, it might be interesting to see because under your conditions, which are far removed from industrial use, whether the nickel, I would guess the reaction rate would step way up, the hydrogenation step.
Yes.
But as you know, people have studied nickel moly for, I was telling Fred, I think 70 years, and still the total mechanism is not fully understood. And your work is very good. Looks like then also begin to putting a small amount of nickel on with your various levels of moly on these bases might shed some more light on the relative role of nickel in the hydrogenation versus the moly in hydrogenation.
That is one of the next experiments that I was having in mind, because we needed to, in order to verify the hydrodenitrogenation, the Hoffman elimination mechanism, in pyridine hydrodenitrogenation, we were able to just verify it by indirectly by analyzing the product of reaction. And the main cause of that was that the hydrogenation of the reaction was the rate limiting step. Now, if we can make that the carbon-nitrogen bond cleavage is the rate limiting step, now I can compare both mechanisms, and that is what is now our next step. So yeah, you have a big point in there.
Thank you very much. Diane, you inform us where lunch will be?
Lunch will be in the music room, which is on the lower level, and it is roughly underneath this next room here. So it's on the west side, I guess, lower level. In the music room is what it's called.
If you care to be seated, we'll resume.